Hello, everyone. I am Noura Ibrahim. I am a second-year graduate student at the University of Michigan, and today I'll talk to you about the inner astronomical unit of V1295 Aquila. All right, so for a little bit of background, we've seen over the past 2 decades or so, this exponential growth in the field of exoplanets, mainly detections with missions like Kepler, TESS, and most recently JWST. So it's very great to be able to detect these planets, but we want to understand their origin stories better. And one instrument that was very instrumental in allowing us to understand planet formation better was ALMA, and it gave us beautiful images of really young stars with accretion or disks around them, as young as about 100,000 to 1,000,000 years. So what we want to study is are these disks. Mainly, we are focusing on this Herbig disk. And Herbigs are special because they have this high luminosity and strong excess emission in near infrared and millimeter wavelength. And because of the high luminosity and the young age, we're able to observe the accretion and planetary formation better. And we see most of this accretion coming in from the inner astronomical units. But because of their really large distances away, we need milli-arcsecond resolution to be able to resolve them, which is why we turn to Chara and VLTI. So the Herbig that I'll be talking about today is V1295 Aquila, which is a Herbig BE star of spectral type B9, which is very special because up to about a few weeks ago, we thought it was an A2 star. And it being a B9 star means it's a lot more massive and a lot younger than we actually thought it was. So we caught it at this really young stage of formation. It's very far away, as you can see, it's about 824 parsecs away, but is very luminous, intermediately massive, and almost face on, which is great for imaging and modeling. So pretty underrated object, if you ask me. Right, so to collect data, we coordinated between Chara and VLTI in the summer of 2019 to get observations that will cover from the short baseline to long baselines. And from previous literature, we were able to estimate a rotational period of about 225 days. So we got our data squared visibilities and closure phases using MERC-X at Chara, which with its angular resolution H-band, we're able to resolve a change in a disk about every 13 days. And then we use Pioneer at VLTI, and with this resolution, we're able to resolve a change every 40 days. So we have 6 nights from MERC-X and 7 nights from Pioneer. And we use this information to split the data accordingly into 2 epochs, A and B. So we expect to see this kind of shape for the visibility, where in the short baselines that are provided to us by VLTI, this drop-off will tell us about the disk diameter. And then in the longer baselines, we are looking for this bounce that will tell us about the sharpness of the rim. So past results from Setterholm et al. In 2018 that Ben talked about a little bit, they attempted to do that for this object in H-band and K-band, which had data that ranged about 3 years. And the best fit that they were able to get was this Gaussian fit, which told us that they could not find this the cavity which we expected to see. So with our new, more sensitive instruments and better UV coverage, we get this data that we will be working with to model an image. So we have better UV coverage, and we can already see in the visibility up here that we can see some sort of bounce, and our closure phases are non-zero. They're pretty small. You see here, this appears goes 20 to minus 20, but there's still, they still tell us that there is some asymmetry. So we started with geometric models using POMI-RED, and we started with this parabolic model, just fitting the visibilities alone, which means that we're assuming a symmetrical model. So with the donut model, we were able to find a cavity, as we can see here, and we fit the bounces pretty well. However, we're not able to fit the short baselines that well with this model. And we get pretty okay chi-squareds, about 1.5 up here and then 1.7 down here. So what we wanted to do as a next step was to be able to fit the inner and outer radii separately. And with that, we moved on to a new model that is the double sigmoid. And the double sigmoid has this functional form, which has the inner radius with its own scale and the outer radius with its own scale, and we're able to fit these independently. So with this new model, we're able to fit the shorter baselines much better. So for epoch A, we have a chi-square of about 1.1, and for epoch B, it's about 1.4, which is a lot better. We still get the cavity, and we get a much better fit for the diameters. However, these assume a symmetrical model with no azimuthal asymmetry, which is not accurate because, as we said, there are non-zero closure phases. So we attempted to fit the closure phases with many models, but there wasn't any model that really stood out to us being the one that describes the non-zero closure phases. So if we assume that they are 0, for example, the chi-squared of the closure phase, we have 3 for A and 4 for epoch B. But then we introduce some asymmetries and we're not able to get them below 2. So with no model standing out to us, we moved on to imaging. So to image, we used the SPARCO 2014 method of assuming a gray spectrum, but allowing a spectral tilt for the disk and the star. So we fixed the log-log slope of the star to be -4, which we see here in the orange. And then we fit for the slope of the disk, which is in the green. And then when we combine them, we do recover the measured combined flux. So you know, okay, we have a great assumption here. And then one step further to make sure that we have a good approximation going, we fit the different, the same model, but across each wavelength independently. And we wanted to make sure that the fits and the parameters don't change that much. So here we have the inclination, we have the diameter and the thickness, and they're all pretty much staying the same. However, we do have this huge jump in projection angle, which we are reconciling by saying that because our disk is pretty much face on, it's hard to characterize this projection angle. And then we have this weird spike in the chi-squared in the edge of the band, which we want to investigate further later. But with this method, our collaborator, Fabian Baron, was able to give us these beautiful images, which show us that we do have this inner cavity. But one thing that we also see is the structure. And we want to make sure that the structure that we're seeing makes sense because it seems to be rotating. So with the estimation of the rotational period of about 225 days, between epoch A and B, there's an average of 20 days. So with that, we estimate this 30-degree rotation from epoch A to B. So we ask, does this match what we see? Yes, it does, at least according to this GIF here. So we wanted to further investigate this and think about, well, does this make sense? Well, potentially, as we saw from a talk earlier by Copus, in 2020, they studied the innermost few astronomical units of the sample of 68 protoplanetary disks and found that 7 or more than 10% of this sample showed this temporal variability in the brightness distribution. And they characterized it into 2 categories of symmetrical variation and asymmetrical variation, with the symmetrical variation being due to changes in the stellar flux, these changes in the brightness may be due to heating or scattered light. And then the asymmetric variations, which we see, could be due to maybe a companion being there. Maybe there's an asymmetry in the dust density distribution. Maybe there's like some sort of pressure bump out there in the inner rim, or illumination or obscuration of circumstellar material near the disk. So our next steps are going to be to confirm that we do see the structure. It's not just an artifact of the UV coverage, and we're going to do that using correlation analysis. And then we want to investigate the wavelength independence further for more models and figure out what is happening with the chi-squared on the edge of the band. And then we already have some MYSTIC data in K-band that allow us to have a better and bigger look at what the disk looks like. which will tell us more about maybe there's some key information that we are missing. And thank you for listening. I will take any questions.
Questions from the hall? Let me ask those who ask question to tell your name in a clear and slow way, because those who are online, they don't know who is asking.
John Young, thanks for the very nice talk. I had a question about the correlation analysis you mentioned on the last slide. Could you go into a little more detail about how you plan to do that, please?
Yeah, so I kind of already started it, but how we're going to do it is we have that image of epoch A and then rotate B with what we expect and then correlate what, to just find the cross correlation between them and see if it makes sense or not.
Thank you. Any other questions? Yeah, please, Antoine.
I think Conrad was before me, so maybe Conrad, that's your question.
Yes. Thank you for this nice talk, Noura. Can you go back to where you flipped the two images? So yeah, this is, I think, very impressive, and I think you can actually see that there's another spot to the lower left, I would say, which is also moving similarly. So that would be my first observation. While the enhancement to the top left seems to be staying at the same location, I would actually almost claim. So I think you might actually indeed be seeing two different sorts of enhancement, one which is staying at the same location and the others that are actually moving. So indeed, following this up would be, sounds very interesting. Yeah. That's all I wanted to comment.
Thank you.
Thank you. Now, Antoine.
This is Antoine Meron from ISO. Yeah, great talk, Noura. I had one question about this this feature that you see. Have you tried to model it in the analytical model, because you only model it in the image, but you could model it as an azimuthal variation, or by introducing a hotspot, and you can see if it moves as well.
So we did do that. We introduced a point source in the model to see if we can make sense of what is happening. We also introduced a second azimuthal variation to just to see if maybe there is two bright spots, but we did that before the modeling too, or before the imaging, sorry. But none of them, again, showed that much improvement to the closure phase chi-squared. So that's why none of them just stood out to us being the perfect model to explain what's happening.
But if you want to model something which is very compact, you need to have a lot of harmonics in for the azimuthal variation. So to be able to produce something very, very sharp. But okay, yeah, I guess it's still a work in progress then.
Thank you very much. And any other questions from the whole? If not, then let's thank Noura again. Oh, sorry, the chat. There is a question in the chat. It looked like there was maybe another clump in the ring started to the east and rotating the same sense as the clump you highlighted. Any thoughts on whether you might be seeing two clumps? Actually, it was discussed a little bit before. Yeah,
possibly. We see this multiple open structure. So when we introduced a point source that to try to explain this asymmetry, and we did a grid of chi-squareds, we were able to recover two kind of possible spots for where that point might be, and we found a spot about here or about here. So they're both possible.
Thank you. So that was a question from Jordan Stone, and the last question is from Josef Varga.
Nice talk. Do you have any means to constrain the temperature of the clump?
We just have the ratio of fluxes that comes out from the modeling. So I guess,
because I think that would be very valuable to numerical models.
Right. Yeah. We just have the geometrical models for that.
Okay. And do you have a number? Is it different from the rest of the disk or higher?
The flux, I think.
The temperature.
Oh, the temperature. No, I do not have that. Yeah. We're just assuming the dust destruction number 1500 Kelvin.
Okay.
Thank you. We need to move on. Let's thank Noura again.